And I'd also like to say a few words of dedication to Professor Bimla Buti, who has been one of the leading physicists and a woman physicist who was one of the first fellows of the National Science Academy, and she had a glorious career. She was at IIT Delhi in the physics department in 1968 before moving to the PRL, and our senior colleagues have had interactions with her, and I think it is only fitting that we dedicate this workshop in her memories.
Professor Buti, as was just mentioned, that she was here. She was working with Professor Soda, but before she could be given a formal appointment here, she got an offer from PRL, and that she could resist. Of course, it was given in a very dramatic fashion, as I hear from the stories, and she accepted that, and she went there, and she made a lot of contributions, great contributions, not only in plasma physics, but also in societal philanthropic contributions. And she was the first woman in Sarfelo in physics, and she did a lot of things for science. Even for IIT Delhi also, she has instituted awards for women students in postgraduate streams. And so many things she had done here, and she used to be continuously in touch with us. I've been fortunate to have interacted with her many platforms, not only in physics department here, but also at the NACI Delhi chapter platform, and many other chapters. And she was very, very active here. Only last 2 years that she shifted to Ahmedabad, and she unfortunately passed away there. We were looking forward that she will come back and we'll celebrate her. She just passed 90, I think she became 91, and 90 we could not celebrate her. That she thought she would do that, but unfortunately that could happen.
Physicists who work on relativistic waves, which she did with Nobel laureate Dr. Chandrasekhar, is quite well known. In fact, the title of the talk is inspired by her thesis, which she did with physics. So, I will be talking about relativistic waves, relativistic effects on plasma oscillation. Before I start, she did her doctoral work with Dr. Chandrasekhar at the University of Chicago on relativistic effects on plasma oscillation and two-stream instability. So in this memorial talk, I am first going to talk about some of our recent work on relativistic effects, a part of which heavily relies on Professor Buti's results. So relativistic waves are routinely excited in today's labs, making her work even more relevant today. So after the talk, I will flash some slides which gives glimpses of her life and her work, and then read out some messages which I have received from colleagues. So I begin the talk. So we begin by asking that this talk is not at a very high technical level. So I have tried to remove almost all equations possible. So this is mostly talking. Okay. So first question which comes to the mind is, what is a relativistic wave? So a plasma wave is relativistically intense when it satisfies the parameter E by m omega Pc larger than 1, where E is the amplitude of the plasma wave, omega P is the non-relativistic plasma frequency. Or equivalently, as the electron participates in the wave motion, the energy it gains in one wavelength, if it reaches of the order of its Reschmann energy, then I say the wave is relativistically intense. So such gigantic waves are routinely encountered in many areas of plasma physics and astrophysics, and the ultimate fate of these waves is a subject of intense current research. The first work on relativistically intense plasma waves was done by Ekhagar and Polovin in 56. What they did was they found wave-like solution by solving the relativistic set of fluid Maxwell's equations and found that the waves can propagate in a cold plasma with a certain phase velocity. Now, most of the present day models of femtosecond laser plasma interactions draw inspiration from Ekhagar-Polovin work. So, this was one of the first work on relativistic waves. So, point to note here, the relativity enters in plasma physics in two places. First, when the flow is relativistic, but the constituent particles, the electrons and ions, have non-relativistic motion. And that is the Ekhagar-Polovin. I would call that the Ekhagar-Polovin limit. So it's a cold plasma where the flow is relativistic, but the constituent particles have non-relativistic motion. The other limit is flow is non-relativistic, but the constituent particles have relativistic speeds. So temperature is relativistic, which means that thermal energy becomes of the order of rest matter. And that is the limit where Professor Buti found. And that is I will call that Buti's limit. Okay. So the question now comes that when you excite such gigantic waves in a plasma, what is their fate? The fate is like this. These waves break just like water waves on a sea. So this is a phenomenon which is called wave breaking. The wave breaking occurs when the amplitude of the wave reaches a point such that the crest of the wave overturns. So wave breaking, such a phenomena also happens in plasmas when the amplitude reaches a critical limit. So this critical limit for a cold plasma was calculated by Ekhagar-Polovin, and they showed that when E by m omega c becomes square root of 2 gamma phase minus 1, where gamma phase is the phase velocity, is the relativistic factor associated with the phase velocity of the wave. When this becomes equal to root 2 gamma phase minus 1 square root, the wave breaks. Now, if you look at this formula, you find a very surprising thing. When the phase velocity of the wave becomes close to the speed of light, then gamma phase goes to infinity and electric field can go to infinity. Which means that relativistically intense longitudinal waves can support infinitely large wave amplitude in principle. The question is this in reality true? So what we found that, okay, before I go to our work, Dawson showed one thing, that breaking can occur even if the amplitude of the wave is much below the wave breaking limit. That wave breaks by a process called phase mixing, and phase mixing happens in the following way. Suppose you take plasma oscillations, the plasma frequency is independent of position. So each electron is oscillating about the ion with a frequency which is independent of position. So they are just going back and forth, back and forth, back and forth. Now, suppose your frequency becomes a function of position by whatever reason. Then the following thing happens. Each electron locally moves with a different frequency, and electrons orbits get mixed up, and this is the phenomenon called phase mixing, and the wave breaks. So if you look at the picture, big picture like this, so when plasma frequency becomes phase dependent because of background inhomogeneity or because of relativistic effect, the wave will break even if the amplitude is much below the wave breaking limit. So here I present the plasma frequency formula well known in textbook, 4 pi Ne square by, all of you know this, who have studied plasma physics. So if the density becomes a function of position, plasma frequency becomes a function of position. If mass becomes a function of position because of relativistic effect, then plasma frequency again can become a function of position. Similarly, if the charge becomes a function of position, which happens in say Yang-Mills plasma or in quark-gluon plasma or in dusty plasma, again wave breaking can happen at a limit much below the wave breaking limit. And I guess that even this 4 pi can become a function of position if you take general relativistic things into account. Sometimes I make thought 10, maybe like maybe not. But I know that if you go to cylindrical oscillations or spherical oscillations, this 4 pi changes become 4 pi by root 4. So it's possible that if there are space-time oscillations, this frequency, this 4 pi can change and become a function of position. So you have, so there is a possibility that by whatever reason, if frequency becomes a function of position, the wave will break. So we studied in the limit where the plasma is cold, phase mixing of an acyl wave. So what we did is initially we loaded a longitudinal wave in a particle in cell simulation, and this is what we saw. That wave, if you just excite, the wave neatly propagates without any problem. Now suppose if you perturb the system, just touch it. What we found that this wave is a very delicate wave, and if you perturb it longitudinally, means giving a velocity perturbation or velocity perturbation in the direction of the wave or opposite to the wave, you see that as the wave evolves, it will show density spikes as it evolves. So this is a sign of wave breaking. The density is going to inflate. So what we did is we calculated the time in which the wave breaks. So you take a acyl wave, excite them in a plasma, perturb it, and wait for some time, and you see that the wave slowly decreases. And that time of breaking depends on the phase velocity of the wave, on the amplitude of the wave, and on the density and the amplitude of the perturbation. So we studied this as a function of amplitude of the perturbation, as a function of amplitude of the wave, and a function of phase velocity, and we found that the wave, our simulation follows the result which we derived for a phase mixing time. So this is a very simple result, but it has enormous applications. Suppose you apply it to a beam which is propagating through a plasma. This is the example of a wave field which is excited by a relativistic beam moving through a underdense plasma. So in the wake of the beam acyl following or relativistic waves get excited, and because of noise in the system, we say that initially the waves are excited, but at a later time you see spikes in the system. So wave is breaking, and this breaking time follows our formula with the phase velocity and the amplitude. Next is we go to the case. So this was the acyl limit where the flows are relativistic, but the constituent particles have non-relativistic temperature. So now I go to the Professor Buti's limit where the flow is non-relativistic, but the constituent particles have relativistic motion. So the temperature is relativistic. So we studied wave breaking in a relativistic warm plasma. This is one of the recent work which we did. Now here there are two limits which one can think which are known. One is when the phase velocity square, gamma phase square times lambda. Lambda is the temperature. When this is much larger than 1, this is called the ultra relativistic. So there is some music coming. Okay. Okay. So lambda is the ratio of thermal energy to the rest mass energy. So in the limit, when the thermal energy is much larger compared to the rest mass energy, that's called the ultra relativistic. And then another regime which is called the laser wake field regime, where the temperature is low but the speeds are large. So gamma square lambda is much smaller than 1.
Just hold on. Somebody's breaking your talk.
Wave breaking.
Sorry.
Okay. Thank you. So this is one area which has been heavily investigated by different people. So in the warm plasma, this was one work which was done by Price, Schroeder, Katsulis-Mori, Z.M. Schweg, and Bulanov, several others. So what we did, we first said, let's see what others have done. So if you look at the wave breaking limit versus temperature, the blue line is the acyl limit for a cold plasma. Price has evaluated a formula which shows that as the temperature increases, the wave breaking limit it decreases. So higher the temperature, lower is the amplitude that can be sustained by the plasma. Similarly, a similar formula but with a different argument was used by Schroeder and showed that as temperature increases, the amplitude decreases. This is of course expected. This was done in the limit where gamma phase square lambda is much smaller than 1. Maybe I should have shifted the figure. Okay, so in the other limit, which is the ultra relativistic regime, that formula was worked out by Curselis and Mori in 88 and Schroeder in 2005. Again, it showed that as temperature increases, the amplitude of the wave decreases. This is this is similar to what Coffey did for non-relativistic plasma. So as temperature increases, the amplitude of the wave decreases. This is somewhat expected because as you heat the plasma, what happens in wave breaking, the density tries to explode at certain point. So it is a thermal pressure which opposes the peaking of density, and that's why with increasing temperature the amplitude decreases. Now question is, which of this formula is right? Is Schroeder right? Is Klein's right? Is Bulanov right? Is Zedamshan right? We could have plotted many formulas. So what we did, we said, okay, well, let's not worry about who is right or who is wrong.
None of them.
We'll do a simulation. We'll load a relativistic wave with a 1D plasma and then let's see what happens. So that is the question which we asked. The question was, what is the correct wave breaking limit for a relativistically intense wave in a warm plasma? So do the phase mix when disturbed slightly. If the phase mix when disturbed slightly, then you don't talk about wave breaking. You can sit with your formula, but a wave slightly disturbed will break up. Like for example, in the Akazar-Following case, even if you have the limit has become meaningless now because you excite the wave, disturbed it by a small longitudinal perturbation, and the wave breaks. Okay, so limit has no meaning. So we wanted to ask a similar question for a relativistically warm plasma. So this is where Buti's work becomes important. So what we did, we took a 1D plasma, loaded a Akazar-Following wave on a background of Joupner distribution. So it's a relativistically hot plasma. So the background distribution is a relativistic Maxwell, which is called a Joupner distribution. So we took a Joupner distribution, excited Akazar-Following there, and let it go, and let's see what happens. So now one thing which is what you should remember, since the plasma is warm now, the wave itself can break because of can decay because of relativistic damping effect. So we should, if you want to study wave breaking effect, first you should take away relativistic Landau damping from your picture. So what we found that Professor Buti gave a formula for the relativistic Landau damping. So we took a wave, excited it, and saw how it decays, and it shows a very nice fit with the formula which Buti gave in 62. So this was the paper I am talking about. This problem was suggested by Chandrasekhar to Professor Buti for her doctoral thesis work. In fact, at that time, nobody was talking about relativistic waves because you could not excite relativistic waves. There was a laser available in 1962 that you could excite relativistic waves. So now, even that time, they were far ahead of their time. They were thinking about relativistically intense waves in the lab. So now, if you want to study wave breaking, you have to first avoid this regime. So excite a wave which does not undergo Landau damping and then disturb it and then see what happens. So if you look at the distribution function, this distribution function, this flat distribution, this is just a cartoon for a Joupner distribution. So if you look at the regime, Buti showed that if your phase velocity or the relativistic factor, the pointer,
This in the top one center, the red one.
there is no red bar.
In the stick also.
Yeah. Okay. So the Buti worked on relativistic Landau damping, and he showed that if the Lorentz factor associated with the phase velocity of the wave, if it is much larger than 1 of lambda by c, where lambda is the ratio of thermal energy to response energy, then relativistic Landau damping rate is very small. So you can choose a particular temperature, and in the distribution function, you can define regime where you have relativistic Landau damping and avoid that and choose the velocity which is away from this regime. This is a rough regime where you do not have relativistic Landau damping, but you have wave breaking system. And if you go beyond one, you have superluminal waves. So I'm not going to talk about superluminal because superluminal is another story. Okay, so we wanted to see that if you go to this regime where the phase velocity is 0.9 times the velocity of light, so you are avoiding Landau damping and excite such a wave, disturb it, see what happens. So first of all, we have to check whether our excited wave follows the relativistic dispersion relation or not. So this was also worked out by Professor Buti, and she showed that the dispersion relation turns out to be, if you studied your first year plasma physics, the first two terms are called the Bohm-Gross dispersion distribution, right? This is plasma frequency square times 3 times k square beta gamma square. Now, Buti showed that if you include the relativistic effect, the formula has another term. This term was later worked by Pregraro also and several others. But this was first time worked by Professor Buti using relativistic kinetic theory. So what we did, we excited a low amplitude wave, let it travel, measured the frequency, and plotted it as a function of wavelength, and to check whether it satisfies the dispersion relation. And we found that our simulation results match quite well with the Buti's formula. Of course, if you increase the amplitude, then you can see that the pink line, which is for a higher amplitude, it starts showing deviation from the dispersion relation because dispersion relation has been worked out at low amplitude, linearized relativistic way. Similarly, if you try to study frequency as a function of temperature, again you see that the simulation results fit very well with the Buti's formula. So now we are all set now. So the relativistic wave is correct relativistic wave. Now we take such a wave and disturb it. So what we did, we disturbed it. So we add a small amplitude sinusoidal perturbation to this large amplitude Akazar-Polovin wave. So this is, well, I am calling it Akazar-Polovin wave, but this is actually Akazar-Polovin light wave because Akazar-Polovin wave is for a cold plasma, whereas this is for a warm plasma. Okay, so and we found that the resultant electric field breaks at an amplitude which is much lower than the Akazar-Polovin, much lower than the wave breaking limit calculated by Schroeder, Primes, Shane, Bulanov, others. Okay, so they can have their own formula, but they are of no use. Just like Akazar-Polovin limit is of no use. Okay. So what we did is, it is really breaking, so we plotted the Fourier spectrum and we found that as time goes on, the energy which you put in a single harmonic is not really a single harmonic because it's a nonlinear relativistic wave. So there are harmonic, but energy slowly goes into higher and higher harmonic, which is shown by this red line. So from this figure, we observe that as time progresses, higher and higher harmonics get generated, which are absent in the blue line. The blue line is for the original Akazar-Polovin light wave without disturbance, and red line is the Akazar-Polovin light wave with disturbance. So it's a clear information, clear indication of breaking back phase. Another thing to check, when the wave breaks, the energy goes into particles, right? So we plotted the phase space, and we found these are the snapshots of the phase space. And you see that as time progresses, you see energetic electrons getting generated. So this is starts from t equal to 0, 2 pi, 4 pi, and finally at 100 pi, 100 times 2 pi, you see highly energetic electrons getting generated. So after breaking, production of energetic electrons is observed, which is the signature of wave. Final picture. we checked the mixing time or the breaking time as a function of different parameters. Mixing time as a function of delta, which is delta is the amplitude of the perturbation. Mixing time as a function of amplitude of the wave. Mixing time as a function of temperature. And you find that all cases, it follows the Dawson formula, which Dawson had derived for a non-relativistic system. Actually, Dawson's argument is neither relativistic nor non-relativistic. It is basically based on geometry of the wave. So you can, since the geometrical argument, it works both for relativistic and non-relativistic. So we are back to Dawson, and we found that a relativistically intense wave always breaks whether it's a thermal plasma or it's a cold. So finally, I summarize my talk. So in a cold plasma, we have seen that a longitudinal attack following mode is a mode of zero measure. It's a mode of zero measure. You touch it and it breaks. So it breaks when longitudinal perturbed, and it has implications for laser wave field plasma experiment. In fact, till our work was done, people were using Akaza-Kolovin limit to interpret their experimental results. In fact, there are papers in Science which say that wave is broken and this is what the energy of the electrons are, which is absolutely incorrect. Because the wave is broken by phase mixing at an amplitude much below that. So in fact, I think that one should actually relook at those experimental results and see what is the right interpretation. There's a nice story that when Sajjana got the Chandrasekhar Award, in his award statement it was written that relativistic waves do not break because of relativistic effects. Actually, relativistic waves break because of relativistic effects. Which was a wrong statement. It was a newspaper title. Okay, so and a similar thing happens in a warm plasma. So our particle in cell study have been performed in two regimes. Regimes where Landau damping is effective and regime where Landau damping is weak, where wave breaking is dominant. And we showed that amplitude decreases in the regime where the Landau damping is, relativistic Landau damping is important. Amplitude decreases exponentially and it follows Buti's prediction. In the regime 2, where the wave follows relativistic warm plasma dispersion relation, again it follows very well Buti's dispersion relation. Third regime, of course, which is our regime, which is where the wave breaking regime, the wave breaks via phase mixing at arbitrary small amplitude, which is far below the predicted theoretical results when it is subjected to small amplitude. So the take-home message is, whenever you have a relativistic wave with a cold plasma, warm plasma, whatever plasma, you touch it and it breaks. Okay, so my collaborators in this work, I have learned almost everything from Professor Kaur on phase mixing. Professor saying, Amita, this Amita's picture was when she was at IPR. Then Vikrant, I don't know Vikrant is here. Okay, Vikrant, in fact this work started with while interpreting one of Vikrant's simulation results. Okay. So then my students Orgo, Nidhi, Ratan and Prabal Singh Verma, they have all contributed to this work. Thank you very much. So now what I will show is I have a couple of slides which Dr. Sarveshwar Sharma has made. These slides are of Professor Buti's life and work. These are some of the slides which Sarveshwar has made. Her family migrated from Lahore to Delhi during the partition of India. Surprisingly, she was actually an art student. So when she came to Delhi, so she gave an exam and then got admission into BSc Physics. So I think for 1 year she was studying arts. Then she did her MSc in Physics from Delhi University. Went to University of Chicago where she had an opportunity to work with Nobel laureate Professor Chandrasekhar. And this is where she worked on relativistic Landau damping and dispersion relations. So she got her PhD for this work, doctorate degree. So she returned to Delhi University as a teacher for 2 years and later went to US to work at the Goddard Space Flight Center now. On her return from US in early 1968, she joined the Department of Physics, IIT Delhi, as a senior scientific officer. So later in 1969, she was invited to join PRL by Professor Sarabhai, and then the then director of PRL, where she worked for more than 23 years. So she founded the PSSI. I was not aware of that. She founded the PSSI back in 1978 and was its president during 1992 and 93. And she also founded Buti Foundation in 2003 to encourage young scientists, particularly women scientists. So here are some pictures with Chandrasekhar. So she got many awards. In fact, in the morning, everybody said that she was the first fellow of INSA. She got the Lifetime Achievement Award from Chicago University in 1993, I think, 1994, sorry. Lifetime Achievement Award from the University of Chicago. And of course, she got several awards during her career. There are a few quotes from Dr. Buti. She said, I opted for physics, chemistry, mathematics, combination rather than biology for the simple result that I was scared of cutting open frogs. Maybe because I am a vegetarian. Second thing is, I took the decision not to marry because of my habit of doing full justice to my wife and tirelessly pursuing every task I took on. Marriage would have meant not doing full justice either to my family or to my profession. Being single, I was free to focus on my professional communication. Sarabhai did not believe in vertical hierarchy and he gave full freedom and responsibilities to scientists. After retirement, Professor Buti spent 4 years at the Jet Propulsion Laboratory. She did her social work. She also did social work through Buti Foundation, which she founded in 2003. So according to Professor Buti, her mentors were her father Bodharaj and Subramanian Chandrasekhar. These are few pictures from Buti Digital Education Center. I don't know where it is. Is this in Delhi? Buti Digital Education Center. These are pictures.
Mutera, it's in Ahmedabad. Mutera, Ahmedabad.
Mutera. Okay.
Yeah, Mutera, Ahmedabad.
I should have seen it. I am staying in Mutera. Okay.
Oh, yeah.
Okay, so these are few pictures from different events. And here is a TV channel interviewing Professor Buti in July 22. Further pictures. Finally, she is deeply missed and greatly loved. Sorry. Professor Buti has touched our lives, stay in our hearts forever. So now I am going to read out one message which Professor Abhijit Sen has given. You want to read it? I read it? Okay. I'll take some water. So this is a message from Professor Abhijit Sen. So I first met Bimla ji more than 5 decades ago when I started my research career at the Physical Research Laboratory, Ahmedabad. The year was 1971, and Professor Buti was one of the earliest members of a theory.plasma group that Dr. Sarabhai was establishing at PRL. I was the last one to join. We ran into each other in the corridor leading to the faculty canteen, and she was hurrying out after finishing her tea. While I was ambling in, on spotting me, she halted for a minute, looked me straight in the eyes and said, "So you are the new young man to join us." So she called Professor Sen. Okay. So Professor Sen was probably 13 years younger. Okay. Before I could respond, she said, "I know all about you. Vikram has briefed me. Welcome to the group. Let us meet sometime. I am in a rush today." With that, she strode off in quick, firm steps while I looked on in awe. My dazed look as I entered the tea room elicited quite a few chuckles as someone remarked, "I see that you have already had a dazzling experience." As I soon learned, I was not the only one to have experienced that instant impact of her personality. Most of the faculty and the staff at PRL were in awe of her, Her hallowed lineage of being a past student of Professor Chandrasekhar helped to further enhance that feeling of awe. She certainly had an aura about her. As a rookie, I therefore kept my distance from her. However, one day I was asked by the administration to get a signature for a certain facility. What facility I cannot exactly remember now. I entered her office and with some trepidation made my request. She took a quick look at the paper, signed it, and then made me to sit down. Listen, she said, you do not need my signature in this matter. As a faculty member, you have every right to demand this for yourself. In fact, you should assert yourself and not give the bureaucracy an opportunity to dictate. After that, she smiled, chatted with me for quite a while, sharing many personal experiences. I came out of her office with a completely altered perspective of her and a tenfold increase in my admiration for her. Over the next many shared years at PR, I came to appreciate more and more her several qualities of character and admirable talents. She won great respect as a teacher with her clear and precise lectures and disciplined mentoring of graduate students doing research under her. She was one of the earliest to work in the area of solitons. Okay, I have not discussed solitons. Professor Sen has worked in solitons. So she was one of the earliest to work in the area of solitons, an exotic and rapidly developing field at that time, and apply them to interpret nonlinear structures in space plasma. Her lectures and seminars were often peppered with the phrases, as a matter of fact. She strived always to avoid imprecise statements or make dubious approximations. Lessons learned from Chandra. She was also quite forthright in her dealings with people and spoke her mind frankly. A trait that bothered some people and created a wrong impression about her person. In reality, she was a very kind person who deeply cared about people around her, particularly younger people and students under her tutelage. This became more apparent to me on the many occasions that I was with her at ICT 3 years, where she used to regularly conduct a plasma exchange. On such occasions, she would naturally assume the role of a local guardian of all the Indian participants and attend to all their needs and comforts. She would also enthusiastically lead many of us, particularly those craving for spicy vegetarian fare, to her favorite eating joints and then to good coffee places. On one such outing, I had casually mentioned that the coffee served at the ICTP snack bar was always very lukewarm or cold. She immediately asked me to go with her the next time. I wanted coffee. The next day, she went with me to the bar and raising two fingers, told the barman, "Do it cafe latte," and then slightly louder, "More to cafe." The man nodded at her and with a smile, sure enough, we got the piping hot coffee. I immediately told her that I had always ordered my coffee using the exact same frame, but never got the desired result. She gave me her characteristic smile and said, "You must know how to say it." With confidence and conviction. That supreme self-confidence in her abilities and strong conviction in her beliefs were hallmark qualities of her personality that helped her not only in dealing with day-to-day challenges, but also in overcoming major odds in life. We are all aware of the spectacular success she has had in her professional life, a brilliant research profile that has won her international and national recognition. She has been equally successful in her philanthropic activities, a post-retirement engagement that has provided enormous benefits to the plasma community in India and also to the society at large. She has also overcome enormous health issues at various stages in her life to stay strong and committed to her life mission. I recall on one occasion offering her hand to come down a flight of steps, which she quickly brushed aside and descended on her own without even a walking stick. This indomitable spirit of hers is what I have come to admire the most and what must remain a source of inspiration for all of us. For me, the sense of awe that I had felt at our first meeting has not faded in the least, but has increased many folds over the years from her friendship and warm affection. She has certainly been a towering figure in our community who will continue to live in our collective memory and whose works and contributions will remain a source of inspiration. Thank you.
So she said, Rohini says, I'm honored to say these few words in memoriam of Dr. Bimla Buti. When I returned to India after doing my PhD in 1979, Dr. Buti was perhaps the only senior well-known woman in theoretical physics apart from Professor Bhavnamati, about whom I had heard. Admittedly, at that stage, I was just trying to land on my feet in a career in theoretical physics in India, and thoughts of women in physics were not even on horizon for me. Maybe a year or two after this, I went to ICTP to spend the summer, and I met Dr. Buti for the first time when she was the director of summer school in plasma physics. I still remember her quite stern and sari-clad presence, and also remember being impressed by her strong personality and her passion towards science. She sternly told me to work hard and not slack off. Over the years, we kept on meeting, but I must say my conversations with her began in earnest more towards the end of her time in PRN. We discussed not so much physics, but more women in physics or rather science. Her philanthropy and her commitment to excellence in science is visible in very many activities of the Buti Foundation. I had meant to do an oral interview with her to be lodged in the archive of the Indian Academy. She had even agreed, but it was not to be. That will be my lasting regret. I feel there is a lot to learn for all of us from our experiences about being a PhD student of the legendary Chandra, about being one of the very few women who made their mark in Indian physics at the time, and from the experiences when the family moved to India after partition. I'm hopeful of being able to put some material on her in the archives of India's scientists, which are being curated at NCBs. This was from Rohini Godbole. Interaction with her, and my interaction with her was more from the IPA, because as the Buti Foundation awards are given by IPA. So she sent me a mail. So this was about an award which was, and there was clearly in the committee some differences of opinion. And she sent me a mail saying she wants to talk to me. I was very apprehensive, because usually when you discuss with these awards and the family representatives or the trust representatives get difficult to deal with. But her first sentence to me when she called me on the phone was, I'm talking to you as a physicist, not as a foundation representative. And then she said, I will give you my opinion as a physicist, and I want you to convey this to the committee. And she was very clear about the points, and of course, everything later sorted out. But this made a very deep impression on me. I had a fortune to meet her in 2019 in the meeting at Hyderabad, where she was felicitated, and I'm sure Sabindu will talk more about it. She was felicitated and awarded by IPA Hyderabad chapter. It was very impressive to see how she stood, how she what challenges she must have faced. And what made me made much deeper impression was she never liked to talk about that. We had invited her for the talk in 2020 for the first edition of Vigyan Vidushi Summer School, which we have started for the women students who are aspiring to pursue a career in physics. She talked on chaos and fractals. In science, she gave an online talk, and even there where we asked her to talk about something about herself, there was one mantra she kept repeating, and I will keep that, I really will cherish that, is don't give up. That she was very, very emphasizing, and that was a message to all. There was one time, in that lecture, I also noticed that many students actually, because it was online and YouTube, they actually got their parents to see this lecture in order to see what the careers in science meant and what meant it. So I think she was really a role model at very large scale, and I would cherish all the interaction which I had with her.
For me, it is a deeply personal loss, because I have actually known Bimla Buti has been part of our household since I was born, because she was the classmate of my father's sister. And my father's sister's name was also Bimla Bamba, and she was Bimla Buti. So they were in the same class, and there were two Bimlas in the same class. But my father's sister was, unlike my father, was not good at math at all. And Bimla was really good at math and always stood first. And I think my father's sister was probably near the bottom. So we always heard about the legendary Bimla Buti all the way from the time she was in school. And every time we would talk, as I grew up and I would talk about being a physicist, the only example set before me was that of Professor Buti.
I first met Professor Buti in ICTP where in fact she was running these spring colleges on plasma physics, although obviously I didn't meet her during those, but she had been doing those for a very long period of time. I met her one summer when I was there, and it was really nice to see a senior physicist who actually was, as everybody has said, who was actually taking over a senior role, and professor who was encouraging other people. So that was quite inspiring.
She would come and discuss with us about our coursework when we were undergoing the first year coursework. And at that time, I also noticed that she was concerned about our well being, particularly about the women students. And she would occasionally ask us if we were facing any problems. And she was also encouraging us to speak out. And that was the time I felt that she was very sensitive towards women's issues and also towards students' issues in general. As you know, she was the only woman scientist in PRL for a very long time. And for an institute like PRL, where there are so few women faculty even now, I think she has set very high standard for all of us, and we will continue to look up to her.
But I would like to say a few words regarding what she stood for, activities which she started and through her foundation, which she established. And then, of course, she used to support camps, medical camps. She used to support medicines for cancer. She used to support eye operations for the senior citizens. And so many such things apart from establishing computer centers for teaching children who do not have any way to reach the computers. And she has left Meena and myself to carry on this task, and we will continue the activities we have initiated. And feel free to contact us in this regard if any other new activity should be promoted, should be done for the benefit of Bimla Buti Foundation. Will always be ready.